Welcome to qnawire.
Hi everyone, so what we have is a water tank that is open to the atmosphere and it is filled with water. The tank has a diameter of 10 meters and water is filled to a height of 2 meters above the bottom. There is a line that is connected to this tank and that line has a diameter of 10 centimeters, and there is also a pipe length that is 100 meters long through which this water is carried through. We know the friction factor of this pipe is 0.0015, and we know that the velocity at discharge is equal to the square root of 2 times gravity times the height of the water at the time of the tank, all over 1.5 plus F times L over D. What we're asked to find is the velocity at the initial discharge time and the time it takes for this tank to empty. So what we're going to do first is just go ahead and substitute and solve for the initial discharge velocity. So we are given that the initial discharge velocity, or the discharge velocity expression, is equal to the square root of 2 times gz all over 1.5 plus F times L all over D. Now we can go ahead and plug in for these quantities, and we see that this can be simplified down into 0.1212 times gz. Now we can do this for the initial and say that the initial discharge velocity will be when the height is at 2 meters, and we can go ahead and plug that 2 in and say that the initial discharge velocity is found to be 1.54 meters per second. Now that's one part of our final answer. Next, what we're asked to do is solve for the time it takes for this tank to empty. So what we can do is go ahead and solve for the volume flow rate going through this pipe. So we can say that V dot is equal to the area of the pipe times the discharge velocity, and we can say that this is equal to pi d squared over 4 times the square root of 0.1212 gz. Now V dot can also be written as dV dt. So dV dt is V dot. So the differential volume is going to be V dot times dt. So we can go ahead and write this as V dot as pi d squared over 4 times the square root of 0.1212 gz dt is equal to our differential volume. Now, from our conservation of mass, we know that this differential volume has to equal the decrease in the volume of the tank at that time. So therefore, this means that dV is also equal to the area of the tank times the differential height, and that's going to be minus dz. And this is going to be equal to minus pi d0 squared all over 4 dz. Now we can go ahead and set these two equations equal to each other for dV, and what we see is that we have pi d0 squared all over 4 times the square root of 0.1212 gz dt is equal to negative pi d0 squared over 4 dz. And by going ahead and simplifying this, we'll see that this is also equal to negative d0 squared. Well, we'll see that dt is equal to negative d0 squared over d squared times 1 over the square root of 0.1212 gz z to the negative 1/2 dz. So we got this by manipulating these terms shown here. Now what we have is dt in terms of dz. So now what we can do is integrate both sides to solve for the time that it takes to empty the tank. So what we can do is we can integrate both sides from t equal to 0 to tf, and we can integrate our z side from 0 to z equal to z1, 2 meters. And what this allows us to do is it gives us an expression for the final time, tf is equal to 2 times d0 squared all over d squared times the square root of z1 over 0.1212 g. And plugging in for all of these quantities, we see that the time it takes to empty the tank is equal to 25,940 seconds, which is equal to 7.21 hours. And that's our final answer.